Welcome to the History of Simple Things, where we delve into the fascinating history behind the little things that shape our world. Trains are massive machines, often stretching for miles and carrying tons of cargo or hundreds of passengers. With such size and momentum, stopping a train is no small feat. Unlike a car, which can come to a halt within a short distance, a train requires much more time and space to slow down and stop due to its immense weight and speed. But how exactly do train brakes work? The answer lies in a combination of mechanics, physics, and advanced engineering. In this video, we're going to take an in-depth look at how train braking systems function, how they evolved over time, and why they're crucial for both safety and efficiency in railway operations. At its core, the idea behind a train's braking system is similar to that of any other vehicle. The brakes create friction to slow down and stop the train's wheels. However, unlike cars, which typically rely on hydraulic or mechanical braking systems, trains utilize air brakes as their primary method of deceleration. This system uses compressed air to engage the brakes and has become the gold standard for train operations worldwide. The basic concept is this. When the train driver, known as the engineer, pulls the brake lever, air pressure is reduced in the brake pipe, which runs the entire length of the train. This reduction in pressure causes the brake valves on each car to release air from reservoirs, applying the brakes on every wheel. The brilliance of air brakes lies in their simplicity and efficiency. They allow the engineer to control the brakes on each individual car simultaneously, ensuring even braking across the entire train. Moreover, air brakes are fail-safe. In case of an emergency, or if there's a malfunction in the system, the brakes automatically engage. This is because the brakes are applied by a drop in air pressure, meaning any loss of air will cause the brakes to kick in. Train brakes weren't always as efficient and reliable as they are today. In the early days of railroads, stopping a train was a laborious process that involved manual brakes. Each car had its own hand-operated brake, and brakemen had to run along the top of moving trains, turning brake wheels on each car. This was not only inefficient, but also incredibly dangerous, leading to numerous accidents and injuries. The invention that changed everything was the air brake, developed by George Westinghouse in 1869. Before this, trains relied on gravity and hand brakes to stop, which was neither reliable nor safe, especially for longer trains. Westinghouse's air brake system introduced the concept of using compressed air to apply brakes uniformly across all cars, drastically improving safety and control. His system was adopted by railroads across the world and remains the foundation for modern train brakes. Over time, the air brake system has been refined and improved, but the basic principles established by Westinghouse remain the same. The move from manual brakes to air brakes was a revolution in rail safety, enabling longer, heavier trains to be controlled with precision. A modern train brake system is composed of several key components that work together to slow down and stop the train. The first of these is the brake pipe, a continuous pipe running from the locomotive to the last car. The brake pipe serves as the conduit for air pressure, and its pressure level determines whether the brakes are applied or released. In normal operation, the brake pipe is charged with high-pressure air, and when the engineer reduces the pressure by applying the brakes, the system responds. Each car in the train has its own brake equipment, including an air reservoir, brake cylinder, and control valves. The air reservoir stores compressed air that's used to apply the brakes. When the brake pipe pressure is reduced, the control valve on each car opens, releasing air from the reservoir into the brake cylinder. The brake cylinder then pushes brake shoes against the train's wheels, creating friction and slowing the train down. The engineer has control over both the service brake and the emergency brake. The service brake is used for normal operations, such as gradually slowing down or stopping at stations. The emergency brake is reserved for critical situations where the train needs to stop as quickly as possible. In an emergency, the air pressure is dumped from the entire system, causing the brakes to apply at full force on every car. Because the brakes rely on air pressure, the system is inherently safe. Any failure in the air supply automatically triggers the brakes. In addition to the air brake system, many trains today are equipped with dynamic brakes, a secondary method of slowing down the train, especially in electric and diesel-electric locomotives. Dynamic braking works by using the train's electric motors in reverse. Instead of using mechanical friction to slow down the train, dynamic braking takes advantage of the train's momentum. When the dynamic brake is applied, the electric motors that normally drive the train's wheels are turned into generators. These generators convert the train's kinetic energy into electrical energy. The electrical energy is then dissipated as heat through resistors, slowing down the train. Dynamic braking is particularly useful on long downhill stretches where prolonged braking is required. It reduces wear and tear on the air brakes and provides smoother control. However, dynamic braking is not a replacement for air brakes, it's a supplement. Once the train is slowed to a certain speed, the air brakes take over to bring the train to a complete stop. Stopping a train involves significant physics, primarily because of the sheer mass and velocity involved. Trains can weigh thousands of tons and travel at high speeds, so the braking system needs to overcome a tremendous amount of inertia. Newton's first law of motion states that an object in motion will stay in motion unless acted upon by an external force. In the case of trains, that external force is the braking system, which provides the friction necessary to slow down the train. The amount of friction generated by the brakes is proportional to the pressure applied by the brake shoes onto the wheels. The heat produced by this friction is substantial, especially during prolonged braking, and can cause wear on the brake components. Engineers must balance the need for effective braking with the risk of overheating or wearing down the brakes too quickly. The braking system of a train is a marvel of engineering, combining mechanical, pneumatic, and electrical systems to safely bring these massive machines to a stop. From the invention of the air brake by George Westinghouse to the modern use of dynamic braking, train brakes have evolved to meet the increasing demands of rail transportation. Understanding how these systems work not only highlights the ingenuity behind rail technology, but also underscores the importance of safety in an industry that moves millions of people and tons of cargo every day. Next time you see a train rolling down the tracks, remember that stopping it requires more than just pulling a lever. It's the result of a complex and highly coordinated system designed to keep everyone safe. Hey there! Welcome back to the channel. Today, we're diving into something that's often overlooked but is absolutely crucial when you ride a motorcycle: the clutch. If you've ever ridden a bike, you know the feeling when you pull that lever on the left handlebar, but what's really going on? What exactly is the clutch doing when you're cruising down the road or tearing up a trail? And how does it help you shift gears and keep your ride smooth? Well, today, we're going to break it all down. So buckle up, let's shift into gear and talk about clutches and motorbikes. First things first, let's talk about what the clutch actually is. Think of it as a middleman between the engine and the wheels of your motorcycle. Without a clutch, your engine would be directly connected to your wheels, and that's not a good thing. Why? Because the engine is always spinning. But the wheels don't need to spin all the time. For example, when you're at a stoplight, you want your engine to keep running, but you don't want your bike moving. That's where the clutch comes in. It temporarily disconnects the engine from the wheels, letting the bike sit still while the engine stays running. Alright, so you're probably wondering, how does it work? In simple terms, when you pull in the clutch lever, you're telling the clutch to disengage. This separates the engine's power from the wheels. When you release the clutch lever, the clutch engages, reconnecting the engine to the wheels and allowing power to flow through again. This engagement is what gives you the control to start moving from a stop, change gears, or even slow down without killing the engine. To break it down even further, let's talk about what's happening inside the bike. Most motorcycles use what's called a multi-plate wet clutch. Don't worry if that sounds technical. I'll explain. Picture a sandwich, but instead of bread and meat, you've got a stack of metal plates and friction plates. These plates sit inside a special housing and are either pressed together, engaged, or separated, disengaged, depending on whether you're pulling the clutch lever. These plates are bathed in oil, which keeps things cool and prevents too much wear and tear, hence the term wet clutch. So when you pull the clutch lever, it separates these plates, disconnecting the engine from the transmission. When you let go of the lever, the plates are pressed back together, re-engaging the engine with the transmission and allowing you to accelerate or maintain speed. Okay, now you might be thinking, why do we even need this middleman? Well, motorcycles, like cars, operate on gears. Gears let you change the speed and power of your bike without overloading the engine. When you shift gears, say from first to second, the engine's power needs to be temporarily cut off from the wheels so that the new gear can engage smoothly. The clutch is what allows this break in power. Without it, you'd probably stall the bike or at least have a rough and jerky ride. Also, the clutch gives you control when starting from a stop. If you've ever tried to start moving without using the clutch properly, you know that you either stall the engine or you get a jerky, lurching start. Using the clutch lets you gradually feed power from the engine to the wheels, giving you a smooth and controlled launch. There are different types of clutches used in motorcycles, and while most bikes use the multi-plate wet clutch, you may also come across a couple of other types. Wet clutch versus dry clutch. Like we mentioned, most motorcycles use a wet clutch, which is bathed in oil. This makes them more durable and smooth, but they do have some friction losses because of the oil. On the other hand, a dry clutch isn't immersed in oil, which can make it more efficient, but it's also louder and tends to wear out faster. Centrifugal clutch. Some smaller bikes and scooters use something called a centrifugal clutch. This type of clutch engages automatically when the engine speed increases. You don't have to worry about pulling a lever or shifting manually, it's all automatic. These are great for beginner riders because they simplify the riding process, but they don't offer as much control as a manual clutch. Now that we've got the basics down, let's talk about one of the most important things when it comes to riding a motorcycle: clutch control. Whether you're a beginner or a seasoned rider, mastering clutch control is key to smooth riding. It's all about finding the right balance between the throttle and the clutch. When you're starting from a stop, you need to slowly release the clutch while gently rolling on the throttle. This is called the friction zone, and it's the sweet spot where the engine starts to transfer power to the wheels, but not too quickly. If you release the clutch too fast, you'll stall the bike. If you don't release it fast enough, you'll be revving the engine too high. It takes practice, but once you get the hang of it, you'll feel like you're in complete control of the bike. The clutch isn't just for starting and stopping, though. You also use it when you're downshifting or engine braking. When you're riding and need to slow down, instead of just hitting the brakes, you can downshift through the gears while using the clutch. This helps slow the bike more smoothly and reduces wear on your brakes. It's also great for keeping your engine in its power band, which is where it operates most efficiently. When you downshift, you pull in the clutch, shift to a lower gear, and then release the clutch again. You need to match your engine speed with your wheel speed, and the clutch helps you do that without jerking the bike around. This is called rev matching, and it's a technique that, when mastered, makes your riding super smooth. Like any part of your motorcycle, the clutch can wear out or develop problems over time. The most common issue is clutch slippage, where the clutch doesn't fully engage and you lose power to the wheels. You might notice that your engine revs higher, but you're not going any faster. This can happen if your clutch plates are worn out or if there's an issue with the clutch cable. To avoid problems, always make sure to adjust your clutch cable properly. Don't overuse the clutch and try to be smooth with your inputs. Riding aggressively with too much clutch slipping can wear out the plates faster. So, there you have it. That's the clutch in a nutshell. It's one of those things that you might not think about much when riding, but it's working hard behind the scenes to make sure your motorcycle rides smoothly. Whether you're starting from a stop, shifting through gears, or coming to a halt, the clutch is your key to control. By mastering clutch control and understanding how it works, you'll not only become a better rider, but also extend the life of your bike. Hey there! Have you ever been curious about how electric vehicles or EVs actually work? You're not alone. These vehicles are becoming more and more popular every day, but the technology behind them might still seem like a mystery to a lot of people. Don't worry though, today I'm going to break it all down for you in simple terms. We'll look at how these electric vehicles actually move, how they get their power, and most importantly, how you can charge them up. By the end of this video, you'll have a clear understanding of the basics of EVs, and who knows, you might even consider getting one yourself. So let's dive right in. Alright, let's start with the basics. How do electric vehicles even work? When we think of regular cars, or what are called internal combustion engine vehicles, the ones most of us are used to, they get their power from gasoline or diesel. This fuel burns inside the engine to produce the energy needed to move the car. But electric vehicles, they don't need gas at all. Instead, they rely entirely on electricity. The heart of an electric vehicle is its electric motor. Think of this as the car's engine, but instead of burning fuel, it uses electrical energy stored in batteries to produce motion. These motors are incredibly efficient compared to traditional engines. When electricity flows into the motor, it creates a magnetic field. This magnetic field generates a force that turns the motor's rotor, which is connected to the car's wheels. The result? Movement. The cool thing about electric motors is that they provide instant torque. That means when you press down on the accelerator pedal, the power goes directly to the wheels, giving you a super smooth and immediate response. This is why EVs often feel faster and more responsive than traditional cars, even though they might have a lower overall horsepower. It's not just about raw power, it's how efficiently that power is used. Another major difference is that electric vehicles don't have as many moving parts as gasoline cars. Traditional cars have transmissions, exhaust systems, and many components that require constant maintenance and can wear out over time. EVs, they're much simpler in design, which means fewer things can go wrong, and they require less upkeep. Now, you might be wondering, if electric cars don't need gas, where does all the energy come from? The answer is simple. It comes from the battery. The battery in an electric vehicle is essentially like the gas tank of a regular car. But instead of storing fuel, it stores electrical energy. Most electric vehicles today use something called a lithium-ion battery. These are the same types of batteries you find in your smartphone or laptop, just on a much larger scale. They can store a lot of energy for their size, which is why they're the go-to choice for EVs. But just like your phone's battery, they do need to be recharged when they run low. When the battery sends electricity to the motor converts it into mechanical energy, which turns the wheels and moves the car forward. The amount of energy stored in the battery directly affects how far the car can go before it needs to be charged again. This is called the car's range. And different EVs have different ranges depending on the size and capacity of their battery. To keep the battery healthy and long-lasting, EVs are equipped with complex battery management systems that regulate things like temperature and charging speed. These systems help ensure the battery doesn't overheat or get damaged from overcharging, keeping the vehicle running smoothly for many years. Okay, so now that we know the battery is super important, how do you keep it charged? Charging an electric vehicle might seem like a whole new concept, but it's not too different from charging your phone or laptop, just on a bigger scale. EVs can be charged in a few different ways, and this is where things get interesting. There are 3 main levels of charging that you should know about. Level 1 charging. This is the simplest and slowest way to charge an electric vehicle. It's like charging your phone using a regular wall outlet. In fact, Level 1 charging can be done using a standard 120-volt household outlet. While this method is convenient because you can plug in your car at home, it's pretty slow. You're looking at about 3 to 5 miles of range per hour of charging. So, if you have a long commute or you plan on driving a lot, this might not be the most efficient way to charge your EV. Level 2 charging. This level is faster and more efficient. Instead of using a regular household outlet, this method requires a special charging station that delivers more power, typically 240 volts. You'll often find Level 2 chargers at public charging stations, or you can install one at your home. With this method, you can expect to gain about 25 to 30 miles of range per hour of charging. That means if you plug in your car overnight, you could wake up to a fully charged battery, ready to hit the road. DC fast charging. If you're in a hurry and need to charge your EV quickly, DC fast chargers are the way to go. These chargers are found at select public charging stations, often along highways or major roads. They can deliver a huge amount of power in a short amount of time, allowing you to charge your car up to 80% in as little as 20 to 30 minutes. However, not all electric vehicles are compatible with DC fast chargers, so it's something to consider when buying an EV. Now you might be asking, how do I find these charging stations? That's where apps and maps come into play. Many electric vehicle manufacturers offer apps that show you where the nearest charging stations are, how much it'll cost to charge, and even whether the charger is available or in use. It's a bit like finding a gas station, except it's all digital and easier to plan around. Here's another cool thing about electric vehicles. They don't just consume energy, they can also generate it. This process is called regenerative braking, and it's a key feature of most EVs. In a traditional car, when you brake, all the energy from the car's movement is lost as heat. But in an electric vehicle, the motor can actually work in reverse when you slow down. Instead of using friction to stop the car, the motor switches to generator mode, converting the car's kinetic energy back into electrical energy. This energy is then stored in the battery for later use. This means that every time you slow down or coast, you're actually helping to recharge the battery. It's not a huge amount of energy, but over time, it can help extend your range, especially in stop-and-go city traffic. So, that's the basic rundown of how electric vehicles work and how they charge. To sum it all up, electric cars use electric motors powered by batteries, which you can charge at home or at public stations. The simplicity of their design means fewer moving parts, which can mean less maintenance in the long run. Plus, with the added bonus of regenerative braking, EVs are becoming more efficient and eco-friendly every day. If you're considering an electric vehicle, it's an exciting time to make the switch. Not only are EVs cleaner for the environment, but they're also becoming more practical and affordable for everyday drivers. Thank you for joining us on this journey through the history of simple things. Don't forget to like, subscribe, and stay tuned for more stories woven through the smallest details.